From the very beginning, Richard Feynman did not fit the image of what a physicist was supposed to be. While others admired complexity and treated advanced mathematics almost as a sacred language, he was instinctively suspicious of anything he could not explain to himself in plain terms. As a boy, he did not memorize formulas to impress teachers. He took radios apart to see how invisible signals could turn into sound. What mattered to him was not authority, not tradition, not even correctness by reputation, but understanding. If something worked and he could not explain it clearly, then, in his mind, it was not truly understood at all. This attitude followed him into his academic life. At a time when physics was becoming increasingly abstract, Feynman showed an unusual comfort with thinking visually. He did not begin with symbols, he began with pictures in his head. He imagined particles as actors moving through space and time, meeting, interacting, exchanging energy, and then separating again. Where others saw intimidating equations stretching across blackboards, he tried to see a story unfolding. This way of thinking was not taught. It was not encouraged. In many circles, it was quietly dismissed as not RV, yet for Feynman it felt natural, almost unavoidable. The culture of physics in the early 20th century rewarded those who could manipulate mathematics with elegance. To question that culture was risky. Young physicists learned quickly that asking for intuitive explanations could make them seem unsophisticated. Feynman ignored that unspoken rule. He openly admitted when he did not understand something, even if everyone else claimed they did. In seminars, he asked questions that cut straight through layers of formalism, sometimes exposing that others were repeating procedures without real comprehension. This made him unpopular in some rooms, but it also made him impossible to ignore. What separated Feynman from many of his peers was not raw intelligence alone, but intellectual honesty. He refused to pretend. If a theory predicted the right numbers but offered no clear picture of what was happening, he felt uneasy. Physics, to him, was not a game of symbols, it was an attempt to describe reality. And reality, however strange, had to be graspable by the human mind in some meaningful way. This conviction drove him to search for alternative paths of thinking, even when those paths looked unconventional. At the same time, the shadow of giants loomed large over the field. Figures like Albert Einstein had transformed science through deep conceptual leaps expressed in powerful mathematics. Many young physicists tried to imitate that style, hoping to achieve similar breakthroughs. Feynman did not imitate. He respected Einstein deeply, but he did not worship the method. Where Einstein often reasoned through thought experiments framed in precise logical language, Feynman leaned toward mental imagery that behaved almost like animated sketches. He was not trying to outdo the great minds before him. He was trying to think in the way that made the most sense to him. This independence of thought was already visible during his early research years. Faced with problems in quantum mechanics that others attacked with dense formalism, Feynman experimented with alternative representations. He asked what the equations were really saying, stripped of their intimidating appearance. Instead of asking how to solve them faster, he asked how to see them more clearly. That subtle shift in perspective would later prove revolutionary, but at the time it simply marked him as different. In informal settings, Feynman often explained physics using everyday language and rough sketches. He would draw lines on paper, arrows pointing forward and backward, intersections that represented moments of interaction. To an outsider, it could look childish. To those paying close attention, it revealed something profound. He was building an internal model of reality that did not depend on symbolic perfection. He was training himself to see physics rather than merely calculate it. This approach reflected a deeper philosophy. Feynman believed that nature did not care about the notations humans used. The universe did not operate in integrals and differential equations. Those were tools invented after the fact. If a simpler representation captured the same physical truth, then it was not inferior, it was superior. Simplicity, in his mind, was not a lack of depth but evidence of genuine understanding. As he matured scientifically, this mindset hardened into a defining trait. He became comfortable standing alone intellectually, trusting his intuition even when it conflicted with established methods. That confidence was not arrogance, it was rooted in relentless self-testing. He constantly checked his ideas against physical reality, experiments, and logical consistency. When his intuition failed, he adjusted it. When it succeeded, he pushed it further. By thinking with drawings rather than reverence for tradition, Feynman was quietly preparing the ground for a new way of doing physics. He was not yet famous, not yet celebrated, but the foundation was being laid. His refusal to accept opaque explanations, his insistence on clarity, and his willingness to look almost foolish in pursuit of understanding would eventually reshape an entire field. Long before the world recognized his contributions, Richard Feynman was already redefining what it meant to truly understand the laws of nature. As his way of thinking matured, Richard Feynman began to realize that his visual intuition was not just a personal preference, but a powerful cognitive tool. While many of his colleagues relied on established mathematical machinery, Feynman treated mathematics as a servant, not a master. He trusted that if an idea was physically real, it should be possible to build an internal picture of it, even if that picture was imperfect. This belief shaped how he approached every new problem, especially those that others considered too complex to visualize. During his early professional years, Feynman encountered situations where standard methods technically worked but felt disconnected from reality. Calculations produced correct experimental predictions, yet no one could explain what was actually happening between the beginning and the end of a process. To Feynman, this gap mattered. He believed that prediction without understanding was fragile, something that could collapse the moment conditions changed. True comprehension, in his view, came from being able to track a process step by step, even if those steps occurred in realms far removed from everyday experience. This mindset made him unusually fearless. He was willing to abandon familiar formalisms if they obscured insight. When others hesitated to question established techniques, he openly explored alternatives, not because he wanted to rebel, but because he wanted clarity. In doing so, he often arrived at ideas that felt shockingly simple compared to the heavy mathematical structures surrounding them. Simplicity, however, did not mean superficiality. His ideas were grounded in rigorous logic and constant cross-checking against known results. Feynman's personality amplified this approach. He was playful, curious, and deeply skeptical of intellectual posturing. He disliked jargon that existed primarily to impress rather than explain. In conversations, he tested ideas by explaining them aloud, watching for the moment they stopped making sense. If an explanation broke down under casual scrutiny, he considered it unfinished. This habit turned everyday discussions into informal laboratories of thought, where concepts were refined through storytelling, analogy, and mental imagery. Over time, this relentless pursuit of understanding reshaped how he saw his role as a physicist. He did not see himself as a guardian of tradition, but as an explorer of nature's behavior. He accepted that the universe at the smallest scales might be strange, counterintuitive, and resistant to classical logic, but he rejected the notion that it had to be incomprehensible. Strangeness, to him, was not an excuse for obscurity. It was an invitation to develop better ways of thinking. In contrast to the towering legacy of earlier giants, Feynman's contribution was not rooted in grand philosophical unification, but in methodological honesty. He showed that progress could come from asking embarrassingly simple questions and refusing to move on until those questions had satisfying answers. Where others accepted complexity as a sign of depth, he treated it as a challenge to be overcome. This attitude gradually distinguished Richard Feynman from his contemporaries. He became known not just for what he knew, but for how he knew it. His thinking process itself became influential, inspiring younger physicists to seek intuition alongside calculation. Long before his most famous contributions emerged, this internal discipline, thinking in pictures, demanding clarity, and valuing understanding over appearance, had already set him on a path that would quietly transform modern physics. By the middle of the 20th century, physics was facing a problem that few outside the field truly understood, yet those inside felt it constantly. The theories describing the smallest building blocks of nature were astonishingly successful at predicting experimental results, but deeply unsettling at a conceptual level. The equations worked, yet they did so in a way that seemed almost dishonest. When physicists tried to calculate how particles interacted with light and with each other, the mathematics often exploded into infinities. Not large numbers, not difficult numbers, but literally infinite results that made no physical sense. This crisis did not mean that experiments were failing. On the contrary, measurements were becoming more precise, and theory matched them with uncanny accuracy. But behind the scenes, physicists knew they were standing on unstable ground. The calculations required elaborate procedures to cancel infinities against infinities, a kind of mathematical sleight of hand that produced finite answers at the end. Many accepted this as the price of doing business in the quantum world. Others felt uneasy but lacked a better alternative. The theory worked, yet no one could explain why it worked so well despite being so conceptually broken. The tension was psychological as much as scientific. Physics had long been guided by the idea that nature, at its deepest level, should make sense, even if that sense was subtle. The success of classical mechanics and relativity reinforced this belief. With quantum theory, however, the feeling was different. The rules were strange, the interpretations conflicted, and the mathematics seemed to demand blind obedience rather than understanding. Young physicists learned techniques without ever forming a clear mental picture of what was actually happening during an interaction between particles. At the center of this unease was the theory describing how charged particles interact with light. It was supposed to explain simple processes, like how electrons repel each other or how atoms emit radiation. Instead, it produced diagrams of calculation so complex that even experts struggled to follow them from beginning to end. Each additional level of precision introduced new divergences, new infinities that had to be carefully removed. The theory felt less like a window into reality and more like a machine that had to be constantly repaired to keep running. Some of the greatest minds of the era wrestled with this problem. They developed sophisticated mathematical frameworks to control the infinities, refining techniques that allowed calculations to converge on the right answers. These methods were powerful, but they were also opaque. Few could explain them intuitively, and even fewer could say what they meant physically. The gap between prediction and understanding grew wider with each success. In this atmosphere, confusion became normalized. It was common to hear physicists admit, often half-jokingly, that no one really understood the theory, they only knew how to use it. This resignation marked a subtle shift in the culture of science. Understanding, once the ultimate goal, was quietly replaced by effectiveness. As long as the numbers matched experiments, deeper questions were postponed or ignored. Against this backdrop, the legacy of figures like Albert Einstein loomed large. Einstein himself was deeply uncomfortable with the direction quantum theory had taken, criticizing its lack of conceptual clarity. Yet even his objections did not resolve the technical crisis. The field moved forward, but with a sense that something essential was missing. This was the environment into which Richard Feynman stepped. He encountered a discipline that was powerful but internally conflicted, precise but poorly understood. The crisis was not simply about infinities on paper, it was about a loss of intuitive connection to physical reality. Physics could calculate outcomes with astonishing accuracy, yet it could no longer clearly explain the processes that led to those outcomes. That unresolved tension set the stage for a radical shift in how the quantum world would eventually be understood. What made this crisis especially dangerous was not that the calculations were difficult, but that they encouraged a kind of intellectual numbness. When infinities appeared, physicists learned how to subtract them away using carefully defined rules, a process that worked but felt disturbingly artificial. The final answers matched experiments with breathtaking precision, yet the path to those answers resembled a maze filled with traps that everyone pretended were not there. Over time, this created a culture where success was measured by technical skill rather than conceptual insight. Many researchers privately admitted that they did not truly know what was happening during a quantum interaction. They could compute probabilities, scattering amplitudes, and energy shifts, but they could not describe the process in a way that felt physically real. The theory had become a powerful black box. You put equations in, performed a series of ritualistic manipulations, and obtained a result. Questioning what the intermediate steps meant was often seen as unnecessary or even unproductive. This mindset carried a hidden cost. When understanding is sacrificed for calculation, creativity narrows. New ideas become harder to generate because there is no clear mental picture to build upon. The theory becomes something to apply rather than something to explore. Physics, which had once thrived on bold conceptual leaps, risked turning into an exercise in technical endurance. Into this fragile intellectual environment came Richard Feynman, who reacted to the situation not with despair, but with impatience. He did not accept that confusion was inevitable. To him, the presence of infinities was not a mysterious feature of nature, but a signal that something was wrong with the way the problem was being framed. Instead of asking how to remove the infinities, he asked why they appeared in the first place. That shift in questioning was subtle, but it changed everything. Feynman sensed that the crisis was as much about language as it was about mathematics. The formalism being used forced physicists to describe processes in an indirect and cumbersome way. Each calculation lost sight of the physical story behind it. Without a clear narrative of what particles were doing, the mathematics grew increasingly detached from intuition. Feynman believed that if one could describe interactions more directly, the infinities might lose their power. Rather than trying to fix the existing machinery, he began imagining alternative descriptions of the same processes. He asked whether it was possible to track interactions in space and time, event by event, instead of burying them inside abstract expressions. This was a radical thought at the time. Most approaches treated interactions as algebraic objects, not as sequences of physical events. Feynman suspected that this abstraction was precisely what allowed infinities to flourish unchecked. The crisis, then, was not merely technical, it was philosophical. It forced physicists to confront a choice: accept a theory that worked without being understood, or demand a deeper connection between mathematics and physical reality. For many, the first option was enough. For Feynman, it was not. He felt that a theory that could not be explained in clear, intuitive terms was incomplete, no matter how accurate its predictions. This refusal to accept confusion as normal marked a turning point. The crisis of quantum theory became, in Feynman's mind, an opportunity. It exposed the limits of existing methods and opened the door to new ways of thinking. What others saw as an unavoidable mess, he saw as a signpost pointing toward a simpler, more honest description of nature. And it was from within this unresolved tension that one of the most transformative ideas in modern physics was about to emerge. As the tension within physics grew, a quiet divide began to form between those who accepted the dominant methods and those who felt increasingly constrained by them. Most physicists worked within highly formalized systems, mastering techniques that allowed them to compute results with impressive accuracy. Yet this mastery often came at the cost of intuition. The calculations were correct, but the reasoning behind them felt distant, almost mechanical. For a discipline born from curiosity about how nature behaves, this detachment was troubling, even if few were willing to admit it openly. In this environment, conformity was rewarded. Young researchers learned quickly that challenging the established mathematical language could isolate them from the community. To succeed, one had to speak the accepted dialect, even if it felt unnatural. Questions about meaning were quietly sidelined in favor of questions about efficiency. Physics became less about seeing and more about executing. Many adapted, some thrived, but a sense of creative stagnation lingered beneath the surface. Richard Feynman did not belong to this culture of quiet acceptance. He was deeply uncomfortable with approaches that required blind trust in formalism. To him, thinking was an active, almost physical process. He needed to feel the logic of a problem, to move through it mentally, not just manipulate symbols according to learned rules. When a method produced answers without providing insight, he treated it with suspicion rather than reverence. What set him apart was his willingness to think differently even when it meant standing alone. Instead of beginning with equations, he often began with imagined processes. He asked what could be happening in space and time during an interaction, even if the prevailing theories did not describe events that way. This habit was not driven by rebellion, but by necessity. It was simply how his mind worked. He trusted his intuition enough to follow it, even when it led him away from familiar territory. This independence of thought allowed him to see limitations that others overlooked. The dominant methods framed quantum interactions in a way that obscured their temporal structure. Events were compressed into abstract expressions that hid the sequence of cause and effect. Feynman sensed that this compression was not just inconvenient, but misleading. By erasing the narrative of interactions, physicists were losing contact with the very phenomena they sought to understand. He began to explore alternative perspectives privately, without concern for how unconventional they might appear. Instead of asking how to calculate faster, he asked how to think more clearly. Instead of refining existing tools, he questioned whether the tools themselves were shaping thought in unhelpful ways. This shift was subtle but profound. It reframed physics as a problem of representation as much as computation. Crucially, Feynman did not reject mathematics. He respected its power and precision. What he rejected was the idea that mathematics alone constituted understanding. For him, equations were summaries of thought, not substitutes for it. If an equation could not be connected to a mental picture of reality, then something essential was missing. This belief guided his exploration and gave him the confidence to pursue ideas that others dismissed as too simple or too informal. As these ideas developed, they remained largely invisible to the broader community. Feynman was not yet proposing a new framework, only testing his intuition against known results. He checked whether his mental pictures could reproduce established predictions. When they did, his confidence grew. When they failed, he refined them. This iterative process, grounded in honesty and curiosity, slowly carved out a new way of thinking. In choosing to trust clarity over convention, Feynman positioned himself at the edge of a transformation he could not yet fully see. His refusal to think the way everyone else thought was not a rejection of physics, but a reaffirmation of its deepest purpose: to understand nature, not just calculate it. As his private explorations deepened, Feynman began to notice something that reinforced his doubts about the dominant approach. When he tried to explain complex calculations to himself step by step, the mathematics often concealed the physical logic rather than revealing it. The symbols moved correctly, yet the reason they moved that way remained obscure. This realization sharpened his belief that the form of a theory could actively shape the kind of understanding it produced. If the form was too rigid or indirect, it could trap even brilliant minds inside procedures they no longer questioned. This insight led him to a quiet but decisive shift. Instead of treating accepted methods as neutral tools, he began to see them as cognitive frameworks with limitations. They guided attention toward certain aspects of a problem while hiding others. By accepting those frameworks without scrutiny, physicists were unknowingly accepting blind spots as well. Feynman wanted to expose those blind spots, not by arguing against authority, but by rebuilding understanding from the ground up. He experimented with describing interactions as sequences of events rather than static expressions. In his imagination, particles followed paths, met at specific moments, exchanged influences, and moved on. Time was not an abstract parameter buried in equations. It was an active dimension in which things happened. This way of thinking felt more honest to him, even if it conflicted with standard formulations. It allowed him to ask new questions, such as how many different ways an interaction could occur and how those possibilities combined to produce what experiments observed. This approach required intellectual courage. There was no guarantee that these mental constructions would lead anywhere useful. They could easily have remained personal intuition with no formal expression. Yet Feynman persisted, driven by a belief that understanding must be earned, not inherited. He trusted that if a picture captured something real, it would eventually align with mathematics rather than contradict it. Over time, these explorations began to coalesce into something more structured. The mental images he used were no longer vague impressions, but consistent representations that could be translated into precise rules. What started as a way of thinking became a way of organizing calculations. Crucially, this organization preserved the physical story behind the math. Each step corresponded to something happening, not just something being computed. This was the turning point. Feynman realized that he was no longer merely interpreting existing theory differently. He was shaping a new language for it, a language in which intuition and calculation supported each other instead of competing. A language that allowed physicists to see, at a glance, what previously required pages of algebra to infer. The implications of this realization were enormous, though not yet fully visible. Throughout this process, Richard Feynman remained remarkably unconcerned with how his ideas would be received. His focus stayed fixed on whether they made sense, whether they illuminated reality more clearly than what came before. Recognition, approval, and tradition were secondary. What mattered was the quiet internal test he applied to every idea. Could he explain it simply? Could he picture it clearly? And did it connect logically to what was observed? By refusing to let convention dictate his thinking, Feynman demonstrated something rare in science. Progress does not always come from adding complexity or refining existing structures. Sometimes it comes from stepping back, questioning the language itself, and daring to imagine that there might be a clearer way to see what has always been there. In choosing clarity over conformity, he was not just preparing a new tool for physics, but redefining how understanding itself could be achieved. The moment Feynman's ideas began to crystallize into something tangible, they did so in a form that surprised almost everyone who encountered them. Instead of presenting a new set of intimidating equations, he introduced a way of thinking that looked almost deceptively simple. Lines, points, and arrows replaced pages of dense algebra. At first glance, it seemed too elementary to represent the deepest processes of the quantum world. Yet beneath that simplicity lay a precision that traditional methods often struggled to maintain. What made this approach extraordinary was not just that it simplified calculations, but that it restored a sense of physical reality to abstract theory. Each line represented a particle moving through space and time. Each intersection marked an interaction, a moment where something actually happened. For the first time, physicists could look at a calculation and see a process rather than just a result. The mathematics was still there, but it was guided by a visual narrative that kept the physics front and center. This visual language transformed how interactions were understood. Instead of treating quantum events as isolated algebraic expressions, they became part of a larger story composed of many possible paths. An interaction was no longer a single rigid process, but a sum of possibilities, each contributing to the final outcome. This idea aligned naturally with the probabilistic nature of quantum mechanics, yet expressed it in a way that felt intuitive rather than mystical. The power of this method quickly became evident. Calculations that once took weeks could now be organized and understood far more efficiently. More importantly, physicists could see why certain terms mattered and others did not. The structure of a problem revealed itself visually, making errors easier to detect and physical meaning easier to extract. What had once felt like blind manipulation of symbols became a guided exploration of physical processes. Skepticism, however, was inevitable. Many wondered whether such simplicity could truly capture the complexity of the quantum world. Physics had long equated depth with mathematical sophistication, and here was an approach that appeared almost informal. Yet, as results accumulated, the doubts weakened. The new method did not merely reproduce known answers, it clarified them. It showed how different contributions combined, how symmetries emerged, and how certain infinities could be controlled in a natural way. The deeper significance of this development lay in how it changed the relationship between intuition and rigor. Traditionally, intuition was seen as something useful for guessing answers, while rigor was reserved for proving them. Feynman's approach blurred that boundary. Intuition became embedded within the formalism itself. The diagrams were not illustrations added after the fact. They were integral to the calculation. Understanding and computation advanced together rather than in separate stages. This shift had profound educational consequences. Students who previously felt lost in a sea of equations found a way in. They could follow the flow of an interaction, see how terms arose, and develop an internal sense of what quantum processes looked like. The subject remained challenging, but it was no longer opaque. Physics regained a sense of accessibility without sacrificing precision. At the heart of this transformation was Richard Feynman's insistence that clarity was not a luxury, but a necessity. He believed that if a theory could not be represented in a way that preserved its physical meaning, then something essential was missing. The diagrams were not meant to replace mathematics, but to discipline it, to ensure that calculations stayed connected to reality. Over time, this visual language became standard across physics. What began as an unconventional way of thinking evolved into a universal tool, used wherever quantum interactions needed to be understood. Its success demonstrated a lesson that extended beyond physics itself. Complexity does not always require complex expression. Sometimes, the most profound insights emerge when ideas are stripped down to their essentials and rebuilt in a form the human mind can truly grasp. In redefining how quantum processes were represented, Feynman did more than solve technical problems. He reshaped the culture of theoretical physics, reminding it that understanding is not measured by how difficult something looks, but by how clearly it reveals the workings of nature. As the new visual language took hold, its most profound impact became clear in places where traditional mathematics had repeatedly failed. Before this shift, calculations in quantum theory often spiraled into expressions so complicated that even experts lost track of their meaning. Entire pages of algebra could pass without revealing why a particular result emerged. With the new approach, complexity did not disappear, but it became organized. Instead of drowning in symbols, physicists could isolate each contributing process and understand its role within the whole. The key transformation lay in how calculations were structured. Each possible interaction was treated as a distinct contribution, something that could be identified, evaluated, and then combined with others. This modular way of thinking was revolutionary. It allowed physicists to break down overwhelmingly complex problems into manageable pieces without losing sight of the physical story behind them. What once felt like chaos became a controlled sum of clearly defined possibilities. This structure proved especially powerful when dealing with the infinities that had haunted quantum theory for decades. Rather than appearing mysteriously at intermediate steps, problematic terms could now be traced back to specific types of interactions. Physicists could see exactly where divergences arose and how they related to physical assumptions. This clarity made it possible to handle infinities systematically, not as embarrassing artifacts to be hidden, but as signals pointing to deeper structure in the theory. Equally important was the way this method changed intuition. Instead of guessing which terms might matter and then checking the mathematics afterward, physicists could often see the dominant contributions before calculating anything. The diagrams acted like maps, showing where the main paths lay and where minor corrections lived. This saved time, but more importantly, it reshaped how people thought. Understanding preceded calculation rather than following it. As these techniques spread, they altered the rhythm of research itself. Collaboration became easier because ideas could be shared visually. A sketch on a blackboard could convey more meaning than a long derivation. Discussions shifted from, "How do you compute this?" to, "What is actually happening here?" Physics regained a conversational quality that had been suppressed by excessive formalism. The subject felt alive again, grounded in processes rather than procedures. This change also highlighted a deeper philosophical point. Nature, at its core, does not care how humans choose to describe it. The success of this visual framework suggested that the earlier difficulties were not inherent to reality itself, but to the language being used to describe it. By choosing a representation closer to physical intuition, physicists were not simplifying nature, they were aligning their thinking more closely with it. The influence of Serra's Richard Feynman in this transformation was subtle but decisive. He did not claim that his way was the only correct one, nor did he dismiss other methods as useless. Instead, he offered a perspective that restored balance. Mathematics remained essential, but it no longer dominated at the expense of understanding. Calculation and insight became partners rather than rivals. Over time, the new approach proved its robustness. It was applied to increasingly complex systems and continued to produce accurate predictions. More impressively, it adapted to new theories and new discoveries without losing its conceptual clarity. What began as a solution to a specific technical problem evolved into a general way of thinking about interactions in the quantum world. The broader lesson extended beyond physics. It demonstrated that progress often depends not on adding more layers of complexity, but on re-examining the foundations of how problems are framed. When a field becomes trapped in its own formalism, innovation can come from those willing to question the language itself. By doing so, it is sometimes possible to unlock insights that were hidden in plain sight. In the end, the triumph of this approach was not merely that it made calculations easier or theories more elegant. Its true success lay in restoring confidence that the universe, however strange, could still be understood. Not perfectly, not completely, but clearly enough to tell a coherent story. And in that clarity, physics rediscovered one of its oldest ambitions, to describe nature in a way that the human mind can genuinely comprehend. As the influence of this new way of thinking spread, it began to reshape not only calculations but the very attitude physicists held toward nature. There was a growing realization that understanding did not require forcing reality into perfectly polished mathematical structures. Instead, it required humility before the complexity of the universe and honesty about what was known and what was not. This shift marked a quiet philosophical turn. Physics was no longer chasing an illusion of absolute neatness, it was learning to work productively with imperfection. At the heart of this change was the acceptance that nature does not behave according to human preferences for elegance. The quantum world is messy, probabilistic, and often counterintuitive. Earlier approaches had tried to tame this strangeness by hiding it behind layers of formalism. The new perspective did something different. It acknowledged the weirdness openly and built tools that could handle it without pretending it was something else. This honesty turned out to be a strength rather than a weakness. One of the most striking consequences was how uncertainty was reinterpreted. Instead of being seen as a failure of knowledge, uncertainty became a fundamental feature of how the universe operates. The new methods made this visible. They showed that outcomes arise from the combination of many possible processes, not from a single deterministic path. This view did not diminish scientific rigor, it deepened it by aligning theory more closely with experimental reality. This approach also dissolved a long-standing tension between realism and calculation. Physicists had often argued about whether quantum theory described reality itself or merely predicted observations. The visual and process-based language allowed many to sidestep that debate. Rather than insisting on a single, true picture, it offered a framework that connected observable results to to underlying mechanisms in a flexible way. Reality could be approached through multiple complementary perspectives, each shedding light on different aspects of the same phenomena. The cultural impact within physics was significant. Researchers became more comfortable admitting what they did not understand. Discussions shifted from defending established methods to exploring alternative viewpoints. Younger scientists, in particular, found permission to ask intuitive questions without fear of appearing unsophisticated. The field regained a sense of openness that had been constrained by excessive reverence for formalism. This openness encouraged creativity. When the pressure to appear mathematically flawless diminished, new ideas flourished. Physicists felt freer to experiment conceptually, to sketch ideas, test them, discard them, and refine them. Failure became part of the process rather than something to hide. The emphasis moved toward insight rather than performance, toward understanding rather than display. The influence of Richard Feynman in this transformation was deeply personal as well as intellectual. His attitude toward knowledge was contagious. He treated learning as an ongoing process rather than a finished achievement. He openly acknowledged confusion and used it as a starting point rather than a source of embarrassment. This attitude resonated far beyond his specific technical contributions. It modeled a way of being a scientist that valued curiosity above authority. Over time, this mindset affected how physics interacted with other fields. The emphasis on clear conceptual frameworks made it easier to communicate ideas across disciplines. Connections to chemistry, condensed matter physics, and even emerging areas like information theory became more natural. When theories are built on understandable processes rather than opaque formalism, they travel more easily and inspire unexpected applications. Perhaps most importantly, this shift restored a sense of intellectual trust. Physicists could once again believe that their theories were not just calculation machines, but meaningful descriptions of the world. Even when those descriptions were incomplete or provisional, they felt grounded in physical reasoning. This trust did not eliminate mystery, but it made mystery something to explore rather than something to fear. In embracing a vision of science that prioritized clarity, honesty, and intuition alongside rigor, physics reclaimed one of its core ideals. The universe did not become simpler, but our relationship to it became more transparent. Understanding was no longer defined by how difficult an explanation appeared, but by how faithfully it reflected the processes unfolding in nature. This legacy continues to shape how new generations approach the unknown. It reminds them that progress often comes not from imposing order, but from listening carefully to what reality is willing to reveal. By accepting complexity without surrendering comprehension, science moves forward with confidence rather than illusion. And in that balance between humility and insight, a deeper, more resilient understanding of the universe becomes possible. As the full consequences of this transformation became clear, it was evident that its impact reached far beyond a single set of techniques or a particular branch of physics. What emerged was a lasting change in how science itself understood progress. The legacy was not confined to calculations on a blackboard or results in academic journals. It reshaped the mindset of generations who followed, redefining what it meant to truly understand nature. One of the most enduring effects was the normalization of clarity as a scientific virtue. For a long time, difficulty had been mistaken for depth. If an idea was hard to explain, it was often assumed to be profound. This attitude quietly discouraged transparency and rewarded obscurity. The shift introduced a different standard. Depth was no longer measured by how inaccessible an explanation sounded, but by how much reality it revealed. A concept that could be explained clearly was not seen as simplistic, but as genuinely mastered. This change influenced how scientists evaluated ideas. The question was no longer only whether a theory worked, but whether it could be meaningfully understood. Explanations that relied solely on formal manipulation without insight began to feel incomplete. This did not diminish the role of mathematics. Instead, it elevated its purpose. Mathematics became a language for expressing understanding, not a substitute for it. When equations aligned with intuition, confidence in the theory deepened. The educational consequences were profound. Students entering physics encountered a discipline that invited curiosity rather than intimidation. They were encouraged to ask what processes meant, not just how to compute them. This fostered a healthier intellectual environment, one in which confusion was treated as a natural stage of learning rather than a personal failure. The result was a generation more willing to explore, question, and innovate. The influence also extended into how science communicated with the broader world. Ideas rooted in clear physical reasoning were easier to share beyond narrow specialist circles. This openness strengthened the relationship between science and society, allowing complex discoveries to be discussed without distortion or mystique. When understanding is prioritized, trust follows. The public can engage with science not as an arcane authority, but as a human endeavor grounded in reason and curiosity. At the center of this legacy stood Richard Feynman, not as a distant icon, but as a model of intellectual integrity. He demonstrated that admitting uncertainty was not a weakness, but a strength. He showed that asking simple questions could unlock profound insights. His approach challenged the notion that genius must be accompanied by solemnity or opacity. Instead, it revealed that playfulness, honesty, and rigor could coexist at the highest level. This influence continues to shape modern research. New theories are often judged by whether they offer not just predictions, but coherent narratives of underlying processes. Visual models, intuitive explanations, and conceptual clarity are no longer secondary considerations, they are integral to progress. Fields as diverse as particle physics, condensed matter, and information science reflect this shift, building frameworks that aim to be both powerful and understandable. Perhaps the most important aspect of this legacy is philosophical. It reinforces the idea that science is not a finished structure, but an evolving conversation between humanity and nature. Each generation inherits tools and concepts, but also the responsibility to question them. Progress depends not only on solving problems, but on refining how problems are framed. When language becomes rigid, understanding stagnates. When language evolves, insight expands. This perspective encourages humility. It reminds scientists that their theories are approximations, shaped by human ways of thinking. No description is final, no framework complete. Yet this incompleteness is not a flaw, it is what keeps discovery alive. By accepting that understanding is always provisional, science remains open to revision and growth. In the end, the lasting contribution was not a single invention, but a standard of thinking. A reminder that the goal of science is not to impress, but to illuminate, not to dominate nature with formulas, but to listen carefully to what those formulas are trying to say. When clarity, honesty, and curiosity guide inquiry, the universe becomes not less mysterious but more approachable. That is the enduring inheritance of this transformation. It lives in classrooms, laboratories, and conversations wherever people seek to understand how the world works. It affirms that even the deepest truths of reality can be approached with human intuition, provided we are willing to question our assumptions and refine the language through which we see the world.